Okay, what this first line means that anything containing sodium. Okay, perfect. That's a good example, Hugo. Anything containing sodium is going to dissolve in water. So if you have sodium chloride, sodium bromide, sodium sulfate, sodium phosphate, sodium carbonate, sodium thiocyanate, sodium whatever, anything that contains sodium atom, sodium ion is going to be soluble in water. So sodium nitrate, sodium nitrite, sodium phosphide, anything that has sodium. Same thing for lithium. So can you give me examples of other soluble compounds? Give me examples of other soluble compounds, please. Yes, please. Examples? Give me examples of other soluble compounds, please.
Chloride?
Okay, what chloride, please?
Oh, sorry.
Or fluoride, what fluoride? Fluoride, of course, those are ions. I'm asking for compounds that are soluble in water. Ammonium fluoride. And where did you get that ammonium? So basically you are getting this ammonium, right? It's ammonia. If you have ammonium ion in a compound, that dissolves in water. So if you have ammonium ion, that is soluble in water. Yes. If you have, what is that ClO3? ClO3, we don't know if it's going to dissolve or not. ClO3, it's not on that table, so we're going to leave that example for later. That is like, are you talking about chlorate ion or chlorine trioxide? So if it's a chlorine trioxide, it may not dissolve in water. It doesn't dissolve in water. But if you're talking about chlorate ion, ClO3 minus, yes, it will dissolve in water, but that's not a compound, that's ion. So nitrate is not a compound, it's ion. So nitrate, when you say nitrate, but instead of nitrate, if you say sodium nitrate, potassium nitrate, ammonium nitrate, anything that has nitrate is going to dissolve. Calcium nitrate, barium nitrate. So as soon as you see there is nitrate, it's going to be soluble. How do we know it's soluble? Because it's going to contain nitrate. And if it does have nitrate, anything that has nitrate, it will be soluble. So that's going to help us with the balancing ionic equation. And I'm going to give like examples of it to answer that question. Then I will start with the with part 1 of the unit 5. Okay, let me do this. I'm going to have to go to part 1. Okay, and I'm going to get a blank page here to answer your questions, and then we continue on this. Okay, let's say you have a compound, of lead PbNO3, and we have to designate this is as a solid, as AQ. What does AQ means? AQ means soluble in water. Is this compound soluble in water or is not soluble in water? Yes, soluble in water. Perfect. It's going to give me potassium, lead iodide plus potassium nitrate. Okay, there are a couple of questions here. First, we want to make sure that we write the combination of the ions properly. Okay, so this is like a double displacement type reactions, is ionic compounds, as you said. This is a cation, has a 2+ charge. How do I know it's a 2+ charge? Because nitrate has 1- charge. Is taking 2 nitrates, so it's going to be 2+ charge. Nitrate ion has 1- charge, and potassium is a 1+ charge. Iodine is 1- charge. Now, when I'm writing the formula on the other side, I'm going to switch partners. I'm going to give the cation from the first compound to anion from the second compound, and vice versa. So I would do lead with iodine. So if I say Pb, but because it has 2+ charge, iodine has 1- charge, I have to bring 2 iodine. And then I take the potassium with nitrate. Potassium has 1- charge, nitrate has a plus charge, and nitrate has 1- charge. So 1 potassium, 1 nitrate. So that's first writing proper formula. Step 2 is to balance this equation. How many lead I have on the first side or reactant side? 1. On the product side, I have 1. Nitrate, how many do I have on the reactant side? 2. On the product side, I have only 1. I cannot change the subscripts because that's going to change the combination and that's not going to work. I can change the coefficient. So I will put a 2 here as a coefficient for nitrate, because when I put 2 as a coefficient for KNO3, that means 2K and 2NO3. Now, I'm going to count the lead is 1 on each side, nitrate 2 on each side. Now potassium, it's 1 on the first side, and after putting 2 here, 2 on the second part. So I'm going to have to add 2 here. 2 potassium, 2 potassium. Iodine, now I have 2 iodine and 2 iodine. My equation is balanced. Basically, I'm counting each one of them, making sure that they're the same on both sides. Equation must be balanced. I'm only allowed to change the coefficient. If there is no coefficient, that means it's 1. And when you have a coefficient, it multiplies by each of the subscripts. So I have 1 lead, 2 nitrate in this molecule. I have 2 potassium, 2 iodine, 1 lead, and 2 iodine, because there's 1 right here. Okay, next step, which is a long answer to your short question, is putting AQ and S. Okay, is this compound soluble? We already talked about this. That is soluble. Someone said it. This is going to be AQ. How do we know it's soluble? I need an answer. How do we know the first compound is soluble? Because it contains what? Because it contains nitrate, and that table said anything that contains nitrate is soluble. So we refer to solubility table. Have a printout solubility table next to you when you are doing this problem solvings, so you don't have to go back and forth. Okay. Second compound, is it soluble or not? Should I put S or should I put AQ for the second compound? Second compound contains potassium. Anything that contains potassium is soluble. That's why is AQ. So that goes back to that rule. Anything contains potassium is soluble. That's why I put AQ. Now, if I go to the next one, PbI2, in PbI2, I have lead iodide. The rule, it says all iodides are soluble, anything containing iodide soluble, except, okay, it says except lead, mercury, and silver. So if I have lead iodide, PbI2 is going to be solid. If I have AgI, is going to be solid. So being able to read that table is going to tell me, because this is an exception, all iodides are soluble, anything containing iodide is soluble, but if it's lead, mercury, or silver, is going to be not soluble, so I put S here. Potassium nitrate, is it soluble or not? Everyone should know the answer to this because anything containing potassium is soluble. Anything containing nitrate is soluble. So this is double soluble. It is soluble compound. So it is soluble. We have 3 aqueous and 1 precipitate or solid compound forming in here. Now, any questions? Did I answer your question? Melissa, now that you saw the table, I think you got your answer to your question, but I just want to double check, make sure that you got your answer.
He said lead.
Final answer for a balanced chemical equation. Now, if you are going further, do you need like ionic equation for this or molecular equation? This is a balanced molecular equation with everything specified if it's solid or AQ. Do you need ionic? Was there a question for ionic equation? Ask for net ionic. Okay, how do we write the ionic equation here? We can only change the things that anything that is designated AQ to ions. So first we are going to write complete ionic equation. For complete ionic equation, I break down anything that is AQ to ions. So PbNO3 is going to change to Pb2 plus I have nitrate, but there are 2 nitrates. I'm going to write 2NO3 minus. This compound is AQ. I'm going to change to ions. So it's going to be 2K plus and 2I minus. On the product side, if it's solid, if it's liquid, if it's gas, don't touch them. Don't break them down into ions. Only if it's AQ, AQ, AQ. This does not change to ions, so it's going to stay PbI2 solid, okay? And the last one is going to change to ions, K plus and nitrate ion, NO3 ions, okay? 2 plus and then K plus and then NO3 minus. So this is called complete ionic equation. This is ionic, and if you want the net ionic equation, for the net ionic, you are going to cancel the spectator ions, anything that appears exactly the same on the reactant side and product side. Can I cancel lead? No, I cannot cancel lead because lead on the reactant side is Pb2 plus, and the product side is associated with iodine, so I cannot cancel Pb. Nitrate, can I cancel it? Yes, I can cancel nitrate because exact same happens on the product side. And potassium, I can cancel it because exact the same on the product side. Now, after you cancel the spectator ion, whatever is left is known as net ionic. PbI2. This should be like toward the very end of this chapter. It's not part of the chemical stoichiometry, basically. It's more of a chemical reactions. Was this a question in the assignment, the Newton assignment, or it was in the chapter, or it's coming from the lab? I don't know which part. Newton? Okay. Okay, I'm glad that you asked the question. Did they answer your question? Is it clear now what is the net ionic equation? Yes, can I move on? Perfect, perfect. Okay, let's move to the first slide of the unit 5. We want to make sure, so we learned about compounds, if it's ionic or if it's covalent bonded compound. We have the structure formula, we know about the bond angle, we know about the shape of the molecule following that table. So we have to memorize that table in order to determine the shape of the molecules. And if it's like ionic compound, we know the name, how to write the formula and all that. Now, when it comes to combining compounds, we have to combine it. When we combine compounds, we have chemical, we call that chemical reaction. So in a chemical reactions of A plus B or A plus 2B, that gives like a B2, we have to make sure that this, if it gives this compound, AB2, we have to make sure it's balanced. Why is balanced? Because why has to be balanced? Because we have to make sure that the law for conservation of mass is applied to any chemical reaction. That the law for conservation of mass, it says that the mass is not created or destroyed in a chemical reaction. It just changes from one form to another form. So the total mass in both sides of the equation has to be the same. In order to understand and study that and apply that to chemical reaction, we have to know what is the mass of the molecule on the reactant side or the product side. So we have to learn about chemical mass or formula mass for the compounds. What is the formula mass? In order to find the formula mass, all you need is the periodic table and understand the mass for each atom. So if you have the mass of individual molecule or formula unit or molecular mass or molecular weight is the sum of the masses of the atom or in a formula unit or a molecule. So if you have carbon tetrachloride as an example, let's say carbon tetrachloride, 1 carbon, 4 chlorine. What would be the molecular mass for this? What you need, what's the formula mass? What you need is to look for the periodic table. Carbon is 12 in the periodic table. So I'm going to say carbon is 1 carbon times 12. So this is the number of carbon, and this is the mass, atomic mass of the carbon. And chlorine, I have 4 chlorines times 35.5. So I have 4 chlorines and each chlorine is 35.5, and I add this all up and it's going to give me the total mass. So help me here. This is going to be 71 plus 71. That's 142 plus 12, 154. Did I do the mental math correct? 154. Now, 154, the numbers that are in periodic table, they are okay. The numbers are in AMU, and that is atomic mass unit. That is the 1/12 of the carbon 12, or that is the unit that is assigned for the mass of the atoms. So we have, in order to change that to workable numbers, we are going to change the AMU to gram. So 154 gram. This 154 gram is known as the molecular mass or the molecular weight for carbon tetrachloride. And that is going to be gram per mole. So 1 mole of this compound is going to be 154 gram. So molecular weight for the compound or the formula mass for the compound is calculated using periodic table, adding up all the atomic masses based on the number of those atoms in the molecule. Going to use the second example for molar mass. Let's say I use the carbon dioxide. What's the mass for carbon dioxide? What should I do? Carbon, I have 1 carbon in the molecule. I'm not getting responses. Can you please just say a response so I can move faster? Sometimes I wait for you for the response. It kind of slows, but at the same time, I want to make sure at least you can hear me. So atomic mass for carbon is 12, and we have 1 carbon. For oxygen, we have 2 oxygen. Atomic mass for oxygen is 16. Where do I know from? I have used it often and often. So over and over, so too often, so I remember it. Do you have to memorize it? You don't have to memorize it because periodic table will be available, but it does help and makes faster to know atomic mass for simple atoms that you are using too often. So perfect, someone who gave me the answer for the 44, that's great. So 2 times 16, that is 32 plus 12, that is a 44. 44 AMU, and if you say AMU, that is the mass for one molecule. So this is the per molecule. You know, molecule is very small. Mole is Avogadro's number of those molecules. So if we change this AMU to gram, so change the 44 gram is going to be per 1 mole. Any questions about how to find the molecular weight or molar mass? I'm going to look at different example. Al2 SO4 3, just to make sure that you know how to count the atoms in the molecule. Okay, this is just an example to help you for that. Aluminum, how many aluminums do we have? We have 2 times, and aluminum I think is a 27, right? And then for sulfur, how many sulfur do we have? We have, if someone who is ready to answer all of this, you can keep your mic on and just give me the answer. It's going to help. Sulfur, how many sulfur we have? It's 3 sulfur. What's the mass for sulfur? Is 32. Each sulfur is 32. How many oxygens do we have? Is it 4 or 12?
4.
Oxygen. In this molecule, we actually have 4 times 3, that is 12 oxygens, times 16 for each mass. And then when you add all of these numbers together, if you have a calculator, please add it up and give me the answer. Then we would put this as AMU. And then when you have the AMU, that is per molecule or formula unit, because for ionic compound we call it formula unit. And then for the mole, this is a formula unit. For one formula unit, we have this mass. Anybody has
327?
327?
Yeah.
Perfect. 327 AMU for per formula unit, or 327 gram per mole. Good?
Okay.
Perfect.
Wait, sorry, Professor. So the SO4 and the 3, so you multiply the 3 and the 4?
Yes, you see, like when I'm counting, I have 3 SO4s, so that gives me 3S and 12O. So this subscripts that is after the parenthesis, it would apply to each one of them individually. That's why I put this example here. So it's 3 times O4 and 3 times S. So you have 12 actually oxygens and 3S, and the aluminum is 2.
Thank you.
You're welcome. Okay, next, molar mass of a compound. So when we have the formula mass in AM2, you change that to gram, and that is called molar mass. What does molar mass means? Mass for 1 mole. So formula mass is the mass for 1 molecule, but molar mass is the mass for 1 mole. That's basically, changing the AMU to gram. But how to calculate it? You always use the periodic table to add those numbers. So now, if you have the molar mass, you can use the molar mass as conversion factor. So there are 2 numbers, two conversions that it can help you with the conversions. Just remember 10.8 gram of CO2. I'm going to use this slide to explain. So if you have the mass here, when you have mass and you have mole, then you have number of particles. Number of particles. So if you have the mass, you can convert to mole, And from mole, you can go to number of particles. There are two conversion factors that you could use. To go from mass to mole, you need the molar mass. So in order to go from mass to mole, you have to use the molar mass. And in order to go from mole to particle, you would use Avogadro's number, and that is 6.02 times 10 to 23, because 1 mole equals 6.02 times 10 to 23 particles. Now, how would you specify those particles? When you say particles, does it refer to atoms? Does it refer to molecules? Does it refer to formula unit? Well, it depends. For element, if you're talking about element, the particle size is atom. If you have a compound, the particle size is molecule. And if you have an ionic compound, it's going to be formula unit. So we have to be very specific. If you have 1 mole of apples, how many apples would that be? It would be 6.02 times 10 to 23. If you have 1 mole of oxygen, 1 mole of O2, that is equal to 6.02 times 10 to 23 O2 molecules. Okay, diatomic, this is the diatomic molecules. But if you have 1 mole of Al, that is 6.02 times 10 to 23 atoms of Al. So it's just using the right term. It's important to use the right term. Are you referring to element? Then it would be atom. If you're referring to a molecule, a compound is going to be a molecule. So if I put this like CO2, it's going to be CO2 molecules. So, but when you are converting, you have to take this. Let me erase the examples so I can work with this diagram here. I take this mole as a bridge. Okay, this is like a bridge, and you cannot jump over the bridge to go from mass to particles. You have to first go from mass to mole, and then from mole to particle. How would you go from mass to mole? You need to know the molar mass for 1 mole. And if you go from mass to mole, you divide by the molar mass. If you want to go reverse, because you can go from mole to mass also, then you would use the molar mass. But in this case, you would multiply by the molar mass. So if you want to go from mole to particles, you would multiply by, because every mole has this many particles. If you want to go from particles to mole, you would divide by 6.02 times 10 to 23. Okay, with this explanation, let's do the problem that the previous problem, it asks you to find the number of moles, find the number of CO2 molecules in 10.8 grams of the CO2. So what is given there, okay, what is given there is the mass. So you have to first convert to the mole. So let's do this problem first, and then I go back to that because I don't know if you can see the problem or not. This problem, how many molecules are in 50 grams of lead oxide? Okay, what is given? What is given to us is the mass. What would be my first step? I need to convert the mass to what?
To mole.
To mole. And what do I need? What information do I need to convert the mass to mole?
Need to find the number of the PbO2.
We need to find the molar mass for PbO2. Molar mass for PbO2, and the molar mass for PbO2 is given here, so we can use that number. If it was not given to us, we look at the periodic table, find the mass for PB, and you add mass of the 2 oxygens to it. But it's given here, so we can use that. So we start with the 50.0 gram of PbO2. It's very important to write the unit and what you are talking about, okay? Times 1 mole of PbO2, it's 239.2 grams of PbO2. That's what's basically what molar mass means, right? If the molar mass is 239.2, that means 1 mole of PbO2 is 239.2 gram PbO2. If we do this math here, what is going to be canceled is the gram of PbO2 is going to be canceled. And when you do the math, the only unit that is left here is the number of moles. So we have the moles of the PbO2. This question is not asking for moles of PbO2, it's asking for how many molecules we have. So we have to continue to change the number of molecules. If you have the mole and you want to find number of particles, you would multiply that by Avogadro's number. Or you would say 1 mole, because you want to cancel the mole, so the mole goes down. 1 mole of PbO2 is 6.02 times 10 to 23 molecules of PbO2. Now, the mole would cancel, and when you do the math, you will get the answer, the numerical value, the answer. If you can give me that number, that would be great.
1.25 times 10 to the 23rd.
One more time, please.
1.25 times 10 to the 23rd.
23 PbO2. Perfect. Thank you. So we have that number. That is, and does it make sense? So yeah, it does make sense, because how would you make sure that it makes sense? Okay, this is important for you. It says 1.25 times 10 to 23. If you compare this number, okay, compare these two numbers, compare this number and this Avogadro's number, okay, this Avogadro's number. 50 gram is less than 239. That means 50 gram is less than 1 mole of PbO2. You agree with me, right? 50 gram is less than 1 mole of PbO2. So the number of particles that we find here, it must be less than 6.02 times 10 to 23. And it is less than that number. And since it's less than that number, then it sounds correct. If we had here about 119.6, if I had that number, grams, I would say, okay, this is half a mole. And if it's a half a mole, this number of particles should be like half of this. And that would be like 3.01 times 10 to 23. And if I had these two numbers, they would make sense. So if it's less than, this is about like 1/4 of a mole, and this is like 1/4 of a mole, and it makes sense. So I just don't want you to just do the math. Do the math and then look at your numbers and make sure that it makes sense. If you found here -22, what would you say? If you found here -23, would that number make sense?
No.
It doesn't make sense, because when you're talking about mole and Avogadro's number, that is a huge number. You can never go to like a negative number or negative exponent. This cannot be less than 1 molecule. So we want to make sure that the number actually makes sense. You cannot have negative power for number of molecules. Even like 18 grams is very tiny amount of water. Okay, in like 18 grams of water, if you have like 18 grams of water, that is going to be 1 mole of water. And that is 6.02 times 10 to 23 water molecule. So for someone to count this number, it would take like many generations to be able to count all this number of molecules. Is a huge number. That's the number of stars that there are in the universe. So that's like a huge, huge number. So we cannot say, okay, negative number. So as long as the numbers do make sense. Any questions about going from mass to number of particles?
Wait, so from grams to a molecule, you divide the grams by the molecule, by the thing that's given times
the molar mass.
The molar mass. Yeah,
mass
by the
for
mole.
1 mole, because you want to change that to mole. And you cannot bypass this. It has to be, the mole is like a bridge. You have to go to mole and then from mole to particle. You cannot go straight from gram to particles.
Okay. Okay, thank you.
So you go from mass to mole first and then to particles. As long as you know that 1 mole is Avogadro's number of molecules, and then 1 mole equals to the formula mass of that compound is expressed in gram, or 1 mole equals to molar mass in gram.
Okay.
Percent composition, this is just going to help us with the calculating percentage, only one formula, but this percent composition, it can help us with the identification of the compounds sometimes. So what you need is for elemental composition, you want the mass of element, okay? So percent composition for CO2, if we say percent composition for CO2, what does it actually mean? It means that what percent carbon and what is the percent of oxygen in this molecule in CO2. So this is the element. Okay, carbon is element, oxygen is element, and this CO2 is the molecule. In order to calculate percent of carbon, you would say mass of element, mass of carbon over mass of CO2. If no numbers is given, if it doesn't say like 10 gram, 5 gram, whatever, you would assume that as 1 mole. So in 1 mole of CO2, how many carbon do we have and what is the mass of carbon? Because we have 1 carbon in CO2, that is 1 times 12. So it's going to be 12 over the total mass for CO2. We calculate that already is going to be 44. 12 divided by 44 times 100%, and that would give the percent of carbon. Now, if you want to calculate the percent oxygen is going to be mass of oxygen, which is 2 times 16, that would be 32 grams of oxygen, over 44 times 100%, and that equals, can you give me this number, please? One of them, the 12 over 44 or 32 over 44?
27%. Well,
how much?
The 12 over 44, I think it's 27.
27%. Okay,
yeah.
Perfect. Since we only have 2 elements in this compound and the total is going to add up to 100%, I can already calculate this and say, okay, this is going to be 73%, or I can do the calculation. I say 32 divided by 44 times 100, and that's going to be 73%. So percent composition is the mass of element divided by mass of molecule times 100%. So times 100%. Don't forget that part, because that's part of the formula. That's for percent composition. Another example for this molecule, being able to count how many atoms you have in the molecule, how many atoms of carbon you have. You have 2 carbon, 4 chlorine, and 2 fluorine. So you don't just say 12 for mass of carbon, you would have to say 12 times 2 for mass of carbon. So the question here is just for chlorine, what is the percent composition or percent of chlorine in this molecule? First, you have to find the mass for 1 mole of this. And for that molar mass of the C2Cl4, that you have to count 2 carbon, each one is 12. 4 chlorine is 35 each, and then 2 fluorine, 19 each. 203 is the mass for the molecule. So we have this one, 203.8. Chlorine is going to be 4 times 35.5 because we have 4 chlorine in this molecule. So we're going to put this gram, and that's how you calculate the percent of chlorine, is 69% chlorine. Does the number make sense? 69%. If we had 105%, would this number make sense? 1.5%. Would this make sense?
Yes.
No.
No?
105% doesn't make sense. If you're talking about 69 makes sense, yes, this makes sense. But 105% is not, it doesn't make sense. Percent of chlorine in this molecule, this is part that's whole. So this is like a 141, okay? That's 141 gram out of 203 gram is less than the total. So it has to be less than 100, cannot be more than 100. So 69.58, yes, that makes sense, but not the 105. If we had 105, that would not make sense. Percent composition of the calcium chloride. What does it mean, percent composition? We need to know the percent of calcium and we need to know the percent of chlorine. So in order to do that, we have to find the molar mass for the calcium chloride first. So calcium is 40 and chlorine is 35.5. You add them together, that gives you the molar mass for calcium chloride, and that is 110. That's for calcium chloride. Mass for chlorine, it's just, we have 2 chlorine, so it's going to be 70. And the mass for calcium is 40 because we have only 1 calcium. So mass of element over molar mass times 100%. So if you don't have question, I'm going to move to the next slide, next topic, which is like conversions in the molecular formula, what can be used. Mass of hydrogen in 1 gallon of water. How much of the 1 gallon of water is hydrogen? How many grams would be hydrogen and how many grams would be oxygen, basically? So first thing you can do, you cannot say 1 gallon doesn't make sense to mass and mole and that. So you have to first find the mass of 1 gallon. How do you find the mass of 1 gallon? You would say, okay, volume for the 1 gallon is 3.78 liter. And then you multiply that by density, that gives you the mass. Because the density is gram per milliliter, you have to convert the liter to milliliter first. So you have the milliliter of 3.785 milliliter of water. And since every milliliter is 1 gram, So you just change that to G, that would give you the number of grams of water molecule or the water in 1 gram of it. And is this hydrogen or this is oxygen? No, that's water molecule. And how much of that is going to be hydrogen? For every molecule, you have 2 hydrogens, 2 grams of H over 18 grams of H2O, because this is the gram of H2O. Then you would cancel the gram of H2O with the gram of H2O. You multiply this by 2, divide by 18. That gives you the gram of hydrogen. So you can use basically percent composition, or you can use the chemical formula as the conversion factor to find the ratio, or you find how much of each you have. With lots of examples that you have in Newton assignments, you would actually master this. But if you have any questions about using the formula as a conversion factor, please let me know now.
Yes, I don't understand.
You don't understand. Okay. So let's take this example to help you with that. We have, okay. How many grams of sodium are in 6.2 gram of NaCl? So we have NaCl, okay? NaCl is, Na is 20. What's the molar mass for NaCl? NaCl, to calculate the molar mass for NaCl, we say sodium is 23, chlorine is 35.45, or I'm going to just use the 23 and 35.5 for simplicity. So sodium chloride is 1 mole of sodium chloride equals 23 plus 35.5, and that is equal to 58.5 grams. So 1 mole NaCl equals 58.5 grams. So if we have 58.5 gram of NaCl, okay, how many grams of Na? How many? How many grams of Na if we had 58.5 grams of NaCl? How much of that would be sodium? Because sodium chloride is made of sodium and chlorine.
23.
23. It would be 23 grams. And how many grams of chlorine? That would be 35.5 grams of chlorine. So for every 58.5 grams of sodium chloride, we have 23 grams of sodium, and we have 35.5 grams of chlorine. So that ratio becomes kind of a definition. So 23 grams of sodium in 58.5 grams of NaCl. So this becomes standard for us. This is the ratio of element to compound. And 33.5 grams of chlorine in every 58.5 grams is like when you have 5%, means like 5 grams of this and the other 95 is something else. But for every 100 grams, you have 5 grams of that. For every 58.5 grams of NaCl, you have 23 grams of sodium. So here, the question is asking how many grams of sodium are in 6.02 grams. We don't always deal with 58.5 grams. So if it's 10 grams, if it's 6.2 grams, if it's more or less, we can use this as a ratio. So if I start with that 6.2, if I start with 6.2 grams of sodium and multiply by this, what do I get? Sodium chloride, NaCl. Because I have the 6.02 gram of NaCl. If I start with the 6.2 grams of NaCl and multiply by this, gram of NaCl would cancel with gram of NaCl, and I have to do the math. Can you do the math and tell me the answer? The answer should be less than 6. Why it has to be less than 6? Because we are only looking at the mass of sodium. How much of this is sodium? And how much is that chlorine?
Wait, you're multiplying the 6.29 times the 58.59? Or
This
the
is a
20?
gram. Okay,
Yeah.
this is a G.
Yeah.
That's gram. And this is a gram.
Oh, okay. So 6.2
Times 20
times
to
20.
divide by 58.5.
Okay. 2.4.
2.4 units.
Yeah.
What would be the units? You see the gram and ACl
All right.
is
Yeah.
canceled with gram and ACl. This would be gram and A.
Okay.
So out of 6.2, 2.4 gram is sodium, and whatever is left is going to be chlorine. That's not the question in this problem, so we don't have to figure out, but it should make sense. 2.4 gram of it is sodium, and what is left is going to be chlorine. Does it make sense?
It makes sense.
Is it better? Any questions? Anyone in class? Any questions?
Well, practice makes perfect.
Yes, practice is going to, that's why we have those Newton assignments to trying to help you with that. And that's why I'm here to help you when you have a question that is, not making sense or for any reason. Okay, for the empirical formula, empirical formula is a practice you did in the experiment 3 of the lab also, is the lowest whole number ratio for the lowest whole number ratio of the element in a compound. So what does empirical formula means for like H2O2? This is if this is the molecular formula, it shows how many different type of atoms we have and how many of each different type of elements and how many of each exact numbers. But this is the molecular formula. And then for empirical, it would be H1O1. So empirical is the lowest number ratio of the atoms, and it has to be whole number. For H2O, I don't know why it's not behaving, my pen, but okay. H2O. If the molecular formula is H2O, what would be the empirical formula? Empirical formula also is going to be H2O, because if you try to divide this by 2 and you end up with like H1O.5, that is not allowed. 0.5 is not allowed because it has to be whole number. So it's the whole number ratio, okay, for the empirical formula. How do you find the empirical formula? To find the empirical formula, you always assume that you have like 100 grams of the compound. So if the percent is given, you convert that to gram and you assume with the 100 grams. So you find the moles for each element. And when you have the moles for each element, as you said, this is like steps that you can always refer to it, but we have to do an example in order to, make sense. So you would find the moles for each element. How do you find the mole for each element? Well, you divide the mass for each element, divide by atomic mass from periodic table. So you have mole for each element. Then you divide all the moles by the smallest mole number. Then you examine your numbers. If they are whole number already, good. If they are not whole number, then you have to look the ratio. If the ratio is like a 0.5, you multiply it by 2. If the ratio is like 0.33, you multiply by 3, and then you can work with that number. Okay. So if it's already whole number, you skip this part. So let's look at like an example and apply the the steps. I said, first step, if the percent is given, convert that to gram. Convert it to gram and gram. Can anyone help me with step 2? If you remember, step 2 was convert the mass of element. So we have the mass of element now. Step 2 would be convert the mass of element to moles of element. How do you convert to moles of element? You would say 1 mole of this element equals 12 grams. So you convert to moles. This one times 1 mole of H over 1 gram of, this is the G is a gram, is not 9. Please make sure that you don't read 9. 1 gram of this. And oxygen, it would be times 1 mole of O. Use the 16 gram, it's not the O2, so it's a 16 gram of O. And then you find these numbers. 60 divided by 12, that's 5 grams, 5 moles. And then 4.4 divided by 4.4 is going to be 4.1 divided by 4.48 moles of hydrogen. And oxygen, 35 divided by this is going to be about 2, right? Is a 1 point something. Can anyone give me that number? Or let me bring the calculator on my phone to use it.
2.2.
Okay, let me use my calculator. If you or you give me the number already. If you have the number, give me. If not, 35.53 divided by 16. So I have 2.2. 2. Next step would be divide all of them by the smallest number of mole. Which one is the smallest number of mole? Would be 2.2. So I'm going to divide all of them by 2.2. 2.2, and this divided by 2.2. Okay, so this is going to give me 1. That's the easiest one. I take care of that part. This one is about 2, right?
Yes.
And this one is like 2.5. What is
Yeah.
the number?
2.2. Around 2.27 or 2.2.
Okay. So what does the initial numbers that we had for the mole for each element? We actually had like carbon with 5, and then hydrogen 4.48, and we had oxygen 2.2. And then we simplify this, okay? We simplify that because this is not the lowest ratio. So we change that to lowest ratio of 2.27. Then hydrogen is 2 and oxygen 1. This is the lowest ratio that we found. Now for this compound, if it's 2.5, like 2.7, this is like close to 2.5. Should I leave like this, or should I go to the, multiply this by a number? This is like too much to ignore it. If it's less than 0.1 difference, we would ignore it. But since it's a 0.25, this is closest to the one that it says 0.25. So because it's closer to that, I'm going to multiply all of them by 4. Okay, so this is going to be multiply them all by 4. Carbon 2.25 times 4.
9.08.
Huh?
9.08.
Okay, so I found it C9 instead. So I found it C9 times 4, H8 and O4. So we have C9, H8 and O4. If you can. Okay.
Your screen went away.
I don't want going to. Do this first. Okay. So since 2.27 was not acceptable, I multiplied every number by 4 and I got this number. So I multiplied this by 4, multiply by 4, and multiply by 4. These are the steps. And you have to do like few of these examples on your own in order to get it. But the steps are here, and this is like an example. Okay, questions? If you did all the math correct, that would be the numbers. If we missed any part and the math was not correct, then we are in, we have to check the math, of course. Always double check the math. Based on the numbers that I had and the explanation that we have in this slide, that it says if it's close to like 0.25, then you multiply by 4. I multiplied by 4. But if the math was correct, I mean, the first thing is that the math should have been correct. So I kind of trusted the numbers that I got from you and the mental math that I did. And so I divide this by 1 mole over 12. I just want to make sure that we have our numbers correct. This is a 5, and then this one divided by 1, 1 gram, and that should be, this should be 4.48. And this one, it was divided by 16 gram, and we found it like 2.2 or 2.22. And then from there, we divide everything by the lowest number, which is a 2.22, and this one divided by 2.22, we found 2.25 here, or 27 here, actually, and this was 2, and this was 1. So that's these numbers. Now, because the 2.27 is not acceptable ratio, acceptable number, decimal cannot stay like this. If we had like 2.1 or 2.05, I would just round it up to 2. It has to be whole number. And because it has to be whole number, I multiplied by 4 each one of them to get this combination. Okay. Any questions? Of course, we will continue on this, and I will answer your questions that you have from the